Imagine a world where every tweet, every book, and every whispered word transforms into a wellspring of knowledge. NLP is not merely a technological tool, it's a magician, turning the chaotic sea of text data into meaningful pearls of wisdom. It's a bridge to understanding the complexities of human language, unraveling mysteries hidden in vast text, from internet forums to ancient manuscripts. In this course, you will explore how this magic is made real. Hi, I'm Apurva Vishnoi, the head of training at Analytics Vidhya, and I will help you understand the machine learning concepts in this course. I have over a decade of experience working in machine learning and AI. Throughout my career, I have worn many hats. I have developed machine learning models to solve industry problems. I have advised companies on setting up machine learning processes, and I have also taught machine learning to CXOs, mid-level, and entry-level professionals. We will begin our journey with recurrent neural networks. Here, we will learn how sequence-based deep learning models can truly enhance the predictions on real-world NLP tasks. Then, we will jump to sequence generation models. We will discuss the problems around these models and their solutions. You will then go on to understand the encoder-decoder architecture, attention mechanism, and the groundbreaking transformers. Understanding these architectures will turn you into an NLP wizard that is in high demand in the AI role job market. So without any further ado, let's begin. Imagine trying to predict whether someone will suggest a game based on the review. This game is bad. As you read each word, your understanding evolves, shaped by the combination of all previous words. This cognitive process closely resembles how a recurrent neural network or RNN functions. An RNN breaks down information into sequences, handling one piece at a time. Each word in our sentence represents a time step. For example, in time step 1, the first word "this" will pass through the hidden layer. In time step 2, the second word "game", along with the output from the previous timestamp, will pass through the same hidden layer. This loop goes on as per the length of the document, integrating past knowledge with the current word. This allows the network to build a contextual understanding. By the time it reaches the final word of the sentence, the RNN has a comprehensive view of the entire review. This game is bad, to predict the sentiment. Let us understand the nuts and bolts of RNN by walking through one hidden layer of RNN. This diagram represents the architecture of RNN. The diagram in the left is the simplified representation of RNN, whereas the diagram on the right is the expanded form of the same structure. Let's first look at the structure of a simple representation of RNN. It consists of an input layer, one hidden layer, and an output layer. Let us now understand how the inputs are processed to give an output in this structure by going through its expanded form. At time step 1, the vectorized form of the first token "this" is passed through the input layer. Let's call it x1. In the hidden layer, the vectorized x1 is multiplied with the weight matrix of the neurons, wx, and then we add bias bh to this product. One thing you must give special attention to is RNNs. Take information from the previous time step to memorize the context. This information is called the hidden state and is denoted by HT, where T stands for different time steps. However, when we calculate the first hidden state H1, there is no previous information to be used. So as a common practice, an initial hidden state, denoted as H0, is initialized to a vector of zeros. For an RNN with n units in the hidden layer, H0 is an n-dimensional vector of zeros as visible on your screens. To consider information at time step t-1, the hidden state of time step t-1 is multiplied with the weight matrix represented as WH, and added to the previous term. The resultant is then passed through an activation function like relu, tanh, etc. to get the information of the sequence at time step 1. This is represented as the hidden state for time step 1 called H1. To summarize, here WX shows the weight matrix connecting the input X to the neural network, and WH represents the weight matrix connecting the previous hidden state. Finally, we get to the output layer. At this stage, the hidden state H1 is multiplied with the weight of the output layer WY, and the bias of the output layer BY will be added to this. And finally, this output will be passed through an activation function, A prime. A prime is often a sigmoid or a softmax activation function depending on the problem statement. Although we have shown the calculation of Y1, it is not necessary to generate this at every time step. Depending on the specific architecture and task, these outputs may or may not be used directly. We will discuss more about this when we talk about different types of RNN later in this module. Another important point to note is that the hidden states captured at each time step are vectors. Think of them as capturing diverse information from word vectors. This information could be regarding quality, gender, emotion, power, enthusiasm, etc. Note that these attributes are only referred as examples. It's very difficult to identify these factors in the actual hidden state. And this is what happens at time step 1 of RNN. Let's now move to time step 2, which is very similar to time step 1. In time step 2, the vectorized input of the second token game will pass through the input layer. Like before, we name it X2, and X2 will enter the same hidden layer just like X1. There, we will multiply it with the weight matrix of the input at time step 2 WX. Now to bring in the sequence, we will add the output from the previous timestamp H1, in this case after multiplying it with WH. To this, we will finally add the bias term BH and apply the activation function. Take a look at the mathematical representation. One important point to note is across the different time steps, the weights WX, WH, and the bias BH will remain the same during forward propagation. Similarly, we will calculate the output Y2 for the second time step by multiplying the hidden state H2 with the weight matrix of the output layer WY. And this sum will be passed through the activation function A prime. Again, WY and BY will remain the same across different time steps. This process continues for as many words or time steps that are there in the document. In our case, we have 2 more words. Hence, we will have 2 more hidden states at time steps 3 and 4 respectively. These are mathematically represented as shown here. The calculation of outputs Y3 and Y4 are also shown here. This is how forward propagation works in RNN. To wrap up, these are the formulas for hidden state HT and output YT at time step T. It is important to note that all the weights and bias represented in these equations are not scalars, but matrices. To get a better understanding of these dimensions, feel free to go through the optional reading material after this video. And with that, we conclude the forward propagation of RNN. Next, let's understand how backward propagation works in RNN. Backpropagation in RNNs is conceptually similar to standard backpropagation used in ANNs. Both techniques are used to optimize the weights of the network by minimizing the error between the predicted outputs and the actual outputs, or in simple terms, by minimizing the loss function. To implement backpropagation through RNN, the network first completes forward propagation through the entire input sequence to compute the outputs. Then, it calculates the loss by comparing the predicted output sequence to the actual desired sequence. The key to backpropagation in RNN is that it goes back through each time step of the sequence, calculating the error gradient at each time step using the chain rule. It is like traveling back in time, and hence, backpropagation in RNN has a fancy name called backpropagation through time. The other details of backpropagation are very similar to ANN. The gradients are used along with the learning rate to update the weights WH, WX, and WY, along with the bias terms. Next, let's understand the different types of RNN. There are 4 types of RNN architectures: many-to-one, many-to-many, one-to-many, and one-to-one. Please note that in these diagrams, the red boxes represent the input layer, each box representing the vectorized inputs at each time step. The yellow boxes refer to the RNN layer, and the blue-colored boxes refer to the outputs. Let us begin with many-to-one. The many-to-one architecture is useful for problems where we need to provide the entire sentence or time series data as input, and we expect an output considering that overall sentence or data. This kind of RNN is used in sentiment analysis, rating prediction, etc. In these problems, the entire review needs to be understood by the algorithm before deciding the sentiment. In many-to-one, the output Y is not received at each time step, like we saw in the earlier diagrams, but is only received in the final time step. Next is many-to-many. There are mainly 2 types of many-to-many RNN model. One, where the length of the input sequence equals the length of the output sequence. And next is where the length of both input and output sequences vary. Let's begin with the first one, where the length of the input sequence equals the length of the output sequence. This model is commonly used in scenarios where there is a direct mapping from inputs to outputs at each time step. For example, part of speech tagging and named entity recognition. Here we input a sequence of words from a sentence, example, they enjoy playing football, and the output will be a sequence of part of speech tags corresponding to each word. For example, prawn, verb, noun. The next is where both the input and output sequences differ in lengths. Example, machine translation. Consider a sentence in English, how are you, as input. In output, we will get its translated sentence in German via get is there. In this case, the input and output sequences differ in length and structure. The model learns to encode the input sequence into a fixed dimensional representation and then decodes this representation into the target language. Next one is just the opposite of many-to-one RNN called one-to-many. Here, non-sequential data like numbers or images are given as input, and a sequential output is generated as output. In one-to-many output, YT at each time step is crucial, as it directly affects the output generated in the next time step. This architecture is used in image captioning, where based on the image, an appropriate title for the image is generated. This is also used in music generation, where by inputting a note, you can generate a symphony. Each output note or chord influences the next output, with the sequence continuing until a stopping criterion is met, like a set number of notes or a specific duration. Finally, we have one-to-one RNN. One-to-one expects non-sequential data in both input and output. Now take a moment to look at this architecture. And does this remind you of something? If you look closely, a one-to-one RNN is nothing but a simple ANN architecture. Next, let's build our first RNN model. Now we will understand how we can use NLP by going through a problem prominent in the video game industry. In the rapidly evolving video game industry, customer feedback plays a crucial role in determining the success and longevity of a game. Reviews, particularly user-generated ones, are a goldmine of insights reflecting the public's reception and satisfaction with various aspects of a game. Pixel Games is a prominent player in the gaming industry. As a gaming company, one of their goals is to drive business growth by analyzing their user reviews that can improve customer engagement and personalized game discovery on their gaming platform. For this, they have collected a data set having 5 different columns, each offering specific insights. These include review ID that uniquely identifies each review, title of the game, year indicating when review was submitted. User review has the text of the user's review and user suggestion has a binary indicator reflecting whether a user would suggest this game to their friends or not. 1 indicates that they would recommend the game, and 0 that they would not. The objective is to develop a model that can analyze pixel game reviews to classify user reviews into recommended or not recommended categories. This is our text classification problem. So with this problem in hand, let us solve this problem.
Now that you have understood the RNN structure in detail, let's solve the sentiment analysis problem for pixel games using RNNs. Let us begin with importing the libraries. You are already familiar with most of the libraries. Now, we will use a code snippet, which is a PyTorch routine that dynamically selects a computational device for executing tensor operations. It checks if a CUDA-enabled GPU is present using torch.cuda.is_available and sets the device variable to CUDA to utilize the GPU's processing powers for faster computation. If GPU is not available, it defaults to using CPU. This device selection is crucial in optimizing the performance of PyTorch applications, allowing them to run efficiently on available hardware by leveraging GPU acceleration when possible or utilizing the CPU when a GPU isn't accessible. Next, let's read the dataset and check their shape. Next, we create a function named preprocess_text. Unlike last module where we did extensive preprocessing, in this module we will keep the preprocessing to a minimum. This function first verifies that the input is a string. Non-string inputs return an empty list to prevent errors. The function then filters the text to retain only alphabetical characters and white spaces, using a regular expression to strip out numbers, punctuations, and special characters. This simplifies the text to essential elements, improving model processing. The text is subsequently converted to lowercase. Lastly, the clean lowercase text is tokenized into words using NLTK's word_tokenize, producing a list of tokens ready for further NLP tasks. This function deliberately avoids removing stop words or lemmatizing to preserve the full context of the data. Let me run this code. Now, let us apply this function to the train, test, and validation data. Let us check if it has been applied on our data or not. As you can see, we have achieved our desired result. Now, let us create the build_vocabulary function, which constructs a vocabulary from a list of tokenized reviews. It assigns a unique index to each distinct word starting from 1. This indexing allows numerical representation of text for deep learning models. The index 0 is reserved for padding. We will understand about it in a while. Now, let us apply the build_vocabulary function to the concatenation of all the user_reviews across the 3 data frames. We will print the first 50 words. We can see that our vocabulary has a length of 1,04,326 words. Now, let us talk about zero padding. Zero padding is beneficial in maintaining a consistent length of input sequences for the model. Zero index is used to fill shorter sequences to maintain uniform sequence lengths. Now, let us create the index and pad_reviews function. It indexes tokenized reviews using a provided vocabulary and truncates them to the specified maximum length of 100. This pads reviews shorter than a length of 100 words with zeros to ensure uniform length for all entries. For example, if a sequence has 80 words or tokens, 0 will be added as the last 20 tokens to make the token length as 100. Additionally, if there are any sequences longer than 100 tokens, they will be reduced till the first 100 tokens. We have given a detailed description of the problem of zero padding below this function. This indexed reviews will be saved in a list. Feel free to pause the video and go through the problem of zero padding. Next, we will convert the user_review column into a list and apply index and pad reviews to this based on the vocabulary we defined above. Now, let's add this list back to our data frames. We can see that the indexed numbers have been added to the data frames against the vocabulary used in the user_review column. Let us visualize a few reviews and their tokens. As you can see from the above results, the first sentence has been truncated, whereas the next two are zero padded. Next, we create the prepare_data function. This takes two inputs, reviews and labels. It converts both of these inputs into PyTorch tensors. The reviews input, which is expected to be already padded, is converted into a tensor of type float. The labels are also converted into a tensor of type float. Finally, the function returns a tuple of these two tensors x and y, which will be used for training. Take a look at the code. Next, we apply the prepare_data function to the train and validation data as well. Now, let's initialize the data loader in PyTorch, which batches and shuffles the training and validation data to facilitate efficient training of deep learning models. It first wraps the training inputs and labels in a tensor dataset for easy access and manipulation. Further, it creates a data loader that iterates over the dataset in batches of a specified size, with an option to shuffle the data at each epoch to reduce model overfitting and improve generalization. Now, we will define the hyperparameters for our RNN model. You can come back to this code and change them to experiment them further. Make sure to go through the comments explaining each hyperparameter. Let's define the sentiment RNN class, which defines an RNN for sentiment analysis. It features a basic RNN layer followed by the tanh activation function, a fully connected layer, and a sigmoid activation function to output probabilities. It processes input sequences and predicts binary sentiments using the last output of the sequence for decisions. Next, we initialize the sentiment RNN model with specified parameters and set up the training essentials, that is, a loss function and an optimizer. The sentiment RNN model is instantiated with defined architecture parameters. NN.BCE_loss is used as a loss function suitable for classification tasks. The optimizer we use is ADAM, a popular choice for training deep learning models, and is configured with the model's parameters and a learning rate. This setup prepares the model for training on sentiment analysis tasks. Now, let us create the calculate_accuracy function similar to what we created in the last module. Further, we will train the model for 30 epochs, tracking and plotting training and validation losses. We will also save the model with the lowest validation loss and later reload it to calculate training and validation accuracies. Let's do that. We can see that our RNN model is clearly underfitting. The reason why we are not getting a good performance with RNN is because the vectorization we used is not capturing the context and meaning of words at all. It is simply giving an arbitrary number to the words. The good news is we can solve this problem using word embeddings.
You have observed that with the word index numbers, RNN was not able to give us a great performance. This is because RNNs are primarily used along with word embeddings. When it comes to large text-based models, the use of word embeddings has almost become a default. So let us learn about word embeddings. You might be wondering, why do we need a new vectorization technique while we already have count vectorization and TF-IDF? Well, while building a bag of word-based models is possible with them, these vectorization methods are not meant for sequence-based models because they don't preserve the sequence and have a high dimensionality. And this is where word embedding comes in while building sequence-based models using deep learning. Word embedding represents words as vectors of d dimensions in a way that captures their meanings, relationships, and context. Every word is represented by a unique list of numbers. Unlike TF-IDF or count vectorizer, these embeddings are generally not derived from the problem we are solving, but derived from training on a large corpus of dataset. Embedding vectors of words which have similar meanings have high similarity. For example, as you can see in the 2D representations of word embedding, the words CEO and board meetings are close to each other. Similarly, the words like legal team and petition are close to each other. The words small and smallest have a relationship similar to the relationship between big and biggest. Three popular methods of creating word embedding are word-to-vec, glove, and fast text. Word-to-vec embeddings were developed by Google in 2013. These embeddings are developed using two methods: continuous bag of words and skipgram. Let's see how continuous bag of words works with the help of this example sentence. Simply continuous bag of words, or CBAW, understands the context through surrounding words and tries to predict the missing word. For example, in the sentence, the CEO delivered a compelling blank at the board meeting. It would try to fill in the blank that is the target word based on the surrounding words like compelling, board meeting, delivered, etc. A feed-forward model would be trained, which would take in as input the surrounding words and try to predict the target word. The CBAW model consists of three main layers: an input layer, a projection layer, and an output layer. The input layer represents the context words. The projection layer learns the word embeddings, and the output layer is used to predict the target word. The input may have one or more words as context. This training is done using sentences from a large corpus of data, such as news articles, Wikipedia articles, web pages, or other text sources. When this training is done on a large corpus of data, the word embedding is able to capture the context of the words. The output layer uses a softmax activation function to give out probabilities of occurrence from all the words in the vocabulary based on the input context. Another approach within the word-to-vec framework is the skipgram. Skipgram takes the opposite approach of CBAW. It uses a word to predict context words. For instance, based on the word presentation, the model would predict associated words like delivered, compelling, or board meeting. The training procedure is very similar to that of CBAW. CBAW is faster and more straightforward, but may sacrifice some accuracy, while skipgram captures more nuanced relationships between words, but requires more computational resources and time to train. Next method is GLOVE. GLOVE stands for Global Vectors. GLOVE was developed as an open source project at Stanford. It uses an unsupervised learning algorithm to generate vector representations for words. GLOVE works by looking at how often each word appears close to other words in a large amount of text, and then uses this information to transform words into numeric forms, so that words with similar meanings have similar vectors. Let's explore step by step how the GLOVE model processes the sentence. The CEO delivered a compelling presentation at the board meeting. The first step is to build the co-occurrence matrix. We start by choosing a window size for the words. For simplicity, we'll use a window size of 1, meaning we consider only the words immediately before and after each target word. Here's how we build the co-occurrence matrix for our example. For the word CEO, the next word is delivered. So we put a 1 next to delivered and zeros elsewhere. For delivered, the adjacent words are CEO and compelling. We mark 1s for both and zeros for the rest. We follow this pattern for each word in the sentence to complete the matrix. Here's the simplified co-occurrence matrix. Note that the diagonal is 0 because a word does not co-occur with itself. This exercise is done on a large corpus of dataset for all the words in the vocabulary. This step is very time-consuming step. This co-occurrence matrix is used to compute a ratio between the probabilities of different words appearing together. For instance, if the word delivered frequently appears in the context of word CEO but rarely appears in the context of word board, this statistical relationship is captured. Glove uses a specific cost function that tries to approximate these ratios using dot products of word vectors. The cost function minimizes the difference between the calculated probability ratios and their approximations based on the learned vectors. The objective function minimizes the cost function to adjust the word vectors. The resultant word vectors are the word embeddings, where words that occur in similar context are closer in the vector space. Next, let's talk about fast text. Fast text was developed by Facebook in the year 2015. Fast text is an extension of the word-to-vec model. It not only provides embeddings of the entire word, but also for n-grams character. That represents word as the average of these embeddings. For example, let's take the English word playing. In the fast text model, playing is not just seen as one whole word. Instead, it is broken down into smaller pieces, like PL, play, play, lie, aying, etc. The key advantage of the fast text embedding is that it can handle rare, new, and even misspelled words. That's all about the popular word embeddings, word-to-vec, glove, and fast text. Apart from these, there are two other embeddings which are used from pre-trained models. They are ELMO and BERT. You will get a better understanding about these and other advanced models later in the course, but let me give a sneak peek. Let's start with ELMO. ELMO stands for Embedding from Language Models. It uses bidirectional LSTM to model language. The network is pre-trained on a large text corpus as a language model, predicting the next word based on previous and future words. The network is trained to predict the next word given the preceding words in one direction, that is forward, and to predict the previous word given the following words in the opposite direction, that is backward. This process helps the model learn how words are used in a variety of contexts. And then comes BERT. BERT stands for Bidirectional Encoder Representations from Transformers. BERT is the state-of-the-art NLP model. There are various versions of BERT which are trained on large amounts of data for specific tasks. The embeddings from these pre-trained models are often used to build other models. We will explore BERT in detail later in the course. And with that, we conclude our theoretical understanding of word embedding.
We will begin with importing the libraries. You are already familiar with most of the libraries. Please note that we will not be running this notebook as these codes may take some time to execute. Once you have successfully imported the libraries, the next step is to check if CUDA is available for running on a GPU or not. Then, let's read the dataset and check its shape. Further, we create a function named preprocess_text just like we did before and apply it on all the data frames. As you can see over here, we have achieved our desired result. Now we will fetch the word embeddings from the word-to-vec function of the GenSim library. We are fetching the embeddings with a dimension of 100. Setting a higher number for dimensionality captures more nuanced relationships between words but increases computational and memory requirements. Using min_count, we can set the words that appear in the vocabulary based in their number of appearances. All words are included in our model's vocabulary since the minimum count is set to 1. The training process is accelerated using 4 worker threads. The size of the model's vocabulary represents the words for which the embeddings were found. And we can see that we have 81,493 vectors converted to vectors using word-to-vec. Now, let's create a function text_to_embedding function. It looks at the sequence of words from our data and fetches the corresponding embedding from word-to-vec embeddings that we just downloaded. Take a look at the explanation for this code. Feel free to pause the video and go through it thoroughly. Now, We will create the prepare_data function. It processes a set of text reviews and their associated labels to prepare them for neural network training in PyTorch. It transforms each review into a fixed length sequence of word embeddings using the above pre-trained word-to-vec model. With a sequence length set to 100, these sequences are then converted to PyTorch tensors of floating point values. Next, let's apply the prepare_data function to both train and validation datasets. Now we have come to the interesting part. Now we will define the hyperparameters. Except for input size, all the hyperparameters are set arbitrarily. You can come back to this code and change them to experiment further. Now let's initialize our data loader in PyTorch. The next step, let us create our model. We will create a sentiment RNN class, which is a recurrent neural network for sentiment analysis using PyTorch's NN.module. It utilizes one RNN layer, leaky ReLU activation, dropout for regularization, and a fully connected layer followed by a sigmoid activation to output the probabilities of a sentiment class. Next, we initialize the sentiment RNN model with specified parameters and set up the training essentials, that is, a loss function and an optimizer. They are the same as before. Further, we will create the calculate accuracy function just like we did before. And then we create the training and evaluation loop exactly like in the previous notebook. The only addition being we have added an early stop with a patience of 3. We can see that our RNN model is clearly underfitting. One of the problems may be because traditional RNN flows only from past to future. It makes predictions based on the preceding context. Let's explore some advanced RNN structures next.
These architectures are multi-layered RNNs and bidirectional RNN. Let us talk about them one by one, starting with multi-layered RNN. Multi-layer RNN is very similar to a simple RNN. It is like a team of experts analyzing a sequence who tackle information step by step. At each time step, each layer takes in two inputs. One, the input from the previous layer, and two, the hidden state from the previous time step. So if we go by our previous sentiment analysis example to understand the review, this game is bad. Then at time step 2 of layer 1, the vector for the word game will be processed along with the hidden state, H11. At the same time, step layer 2 will take the output of previous layer Y12 as the input along with the hidden state, H21 from the previous time step. And this process continues until the last word in the sequence is processed. The outputs of the final RNN layer are the final predictions given out by the structure encompassing the full context passed through multiple layers of comprehension. This collaborative and parallel processing across layers makes multi-layered RNNs adept at handling complex sequential datasets. However, because of the complexity of the structure, training a multi-layered RNN is a time-consuming process. In practice, for simple problems, it is very rare to use more than 3 hidden layers, and sometimes even a single layer does the job. Now let us understand bidirectional RNN. In bidirectional RNN, the network enables it to capture dependencies in both directions. The bidirectional RNN processes the data twice, one while processing the input sequence in the forward direction and the other in the backward direction. This allows the network to access information from past and future time steps simultaneously. Bidirectional RNN enhances the model's ability to capture long-term dependencies and make more accurate predictions in complex sequential data. Let us understand this with an example. In a sentence like, "The bandage was wound around the wound," a unidirectional RNN processing sequentially might incorrectly tag both instances of wound as nouns, missing the verb interpretation in the second instance. In contrast, a bidirectional RNN, considering context from both directions, correctly identifies the first wound as a noun and the second as a verb, demonstrating its ability to capture bidirectional dependencies for more accurate POS tagging. This example highlights how different approaches can lead to divergent POS tagging results, underscoring the advantage of bidirectional models in understanding nuanced linguistic structures. In a bidirectional RNN, we compute hidden states in both forward and backward direction. Hence, each time step will have two hidden states, and the final hidden state is calculated by concatenating these two hidden states. For example, imagine you are dealing with a sentence having four words. At time step 1, the H1 and H'4 will be concatenated to get the final hidden state. Similarly, at time step 2, the final hidden state will be the concatenation of hidden states, H2 and H'3. And this continues for the next two time steps. Now, output is calculated the same way as before, where the hidden state of each time step is multiplied with the weight of the output layer, Wi. Then we add a bias By to this, and the final output is passed through an activation function A', and this same calculation is done for Y2, Y3, and Y4. Let's jump to the Jupyter Notebook next and create a multi-layered and bidirectional RNN model and see if our scores improve.
Let us begin with defining the hyperparameter value for number of layers to 2. We will create the sentiment by RNN class, which defines a neural network for sentiment analysis using a bidirectional RNN with 2 layers. This network takes input sequences and processes them through a bidirectional RNN layer, allowing it to gather context from both past and future data points within the sequence. Then, we initialize the model, loss function, and optimizer just like we did for unidirectional RNN. Now, we train our bidirectional RNN model on the dataset for 30 epochs, save the best model, and print the score. We can see no significant improvement with this approach. In fact, our model is underfitting and performing lower than simple RNN. This may be because of the limitations of RNN, which we have listed below for you. Feel free to pause the video and go through this thoroughly.
To solve the vanishing gradient issue, we have two advanced versions of RNN, GRU and LSTM. In an RNN, the information from the previous state, HT-1, directly influences the current time step. Sometimes, this information may not be very important, or it might get lost when mixed with new data. This is where the GRU comes into play. The GRU can effectively manage which components of the old information to retain and which components of the new information to consider in the hidden state. This selection of information is enabled by something called the update gate. The update gate is used to select components from the previous and current hidden state as per the shown equation. Here, HCAP is commonly referred as candidate hidden state and is similar to how hidden state is calculated in a conventional RNN. HT-1 is the hidden state from the previous time step, while UG is the update gate. In GRU, the final hidden state HT is depicted by this straight line. Here, in the equation, UG represents the update gate vector in the GRU architecture, which can range from 0 to 1. If you look at this equation closely, you will find it is similar to the weighted average equation. If UG is close to 1, the model prioritizes new information from the hidden state over the information present in the previous hidden state. If UG is close to 0, it retains the old information from the previous hidden state and discounts the new information. The update gate is the central innovation in a GRU. Let us understand the complete architectural design of GRU in a step-by-step manner. Starting with the update gate UG. The update gate UG takes in two inputs: the previous hidden state HT-1 and the current input XT at time step T. These are multiplied with the weight matrix of the update gate. A bias is added, and finally, a then sigmoid function is applied to get an output, as you can see in the formula and the diagram. Remember, the value of update gate UG is between 0 to 1 due to the sigmoid activation function. This equation is often represented in a condensed form. Instead of separately considering the weight matrices of the current input and previous hidden state, we can combine them into one weight matrix called WU for the update gate. From now on, we will write other equations in this format. Once the update gate is calculated, it is used to calculate hidden state HT as per the equation that we have already seen. This is also represented in the diagram here. But what about candidate hidden state H cap T referred in the equation and the diagram? Candidate hidden state H cap represents the potential new content that will be part of the current hidden state. Its calculation is very similar to how we have calculated the hidden state in an RNN, with the exception of a gate called reset gate. This is the mathematical representation. In the formula, the current input product of the previous hidden state and reset gate vector is multiplied with the weight matrix. Then we add the bias term, and the resulting output is passed through the tan H function to get an output ranging between -1 to 1. Now we have been introduced with a new term from the equation RG, or reset gate. It's important to know that a GRU, or gated recurrent unit, has two types of gates: update gates and reset gates. We've already talked about the update gate, which is a key feature of the GRU. Now let's learn how to calculate the reset gate. Just like update gate, the reset gate also takes in the previous hidden state, HT-1, and the current input XT at time step T. Then it treats them with the weight matrix of the update gate, adds bias, and then applies the sigmoid function to produce an output like you can see in this formula. And there you have it. This completes the structure of the GRU. This is how information is processed within a GRU. The GRUs make sure that the important information from the previous time step is passed through using the update gate vector while reducing the vanishing gradient problem. It is important to note that the update gate is a vector, so it can control and select which specific information from the previous time step is supposed to be carried forward to the next time step. For example, in a particular dataset, it may be more important to send information regarding emotions and power captured in a word from one hidden state to the next compared to other factors such as quality, gender, power, enthusiasm. Again, these factors are just mentioned as example. It is very difficult to identify them in the actual hidden states. Next, we'll show how to implement a GRU for pixel games.
We will create a sentiment GRU class which implements a bidirectional GRU neural network for sentiment analysis. It features configurable layers, dropout, and leaky ReLU activation. This network processes input sequences, applies dropout, and uses a fully connected layer on the last output, followed by a sigmoid function for binary classification. Now, we will initialize the necessary elements and then train the model. We have got a good fit model with bidirectional GRU with about 83%. Now, let us understand the other types of RNN, LSTM, next.
Long short-term memory, as the name suggests, excels at capturing long-term dependencies or memories from long ago, making it ideal for sequence prediction tasks. If you remember, RNN as an architecture only maintains a single hidden state. Since it is difficult to carry forward the information in an RNN across several time steps, the information captured in the hidden states of RNN is often referred as short-term memory. On the other hand, LSTMs are an extension of RNN. They maintain both the short-term and the long-term memory, making LSTM useful in scenarios where the time gap between the relevant data and the point where it is needed is huge. Like GRU, the LSTMs also use gates to control the flow of information, but it has a more complex architecture. While GRU has two gates, reset and update, LSTM has three: forget, input, and output gates. The forget gate and the input gate in LSTM combined perform the same function as the update gate in GRU. While GRU operates with just one hidden state to pass information across, LSTM maintains two states. the long-term memory called cell state, and the short-term memory called hidden state. The cell state is depicted as a straight line at the top in the diagram. It is updated using outputs from the forget and input gates as shown in this equation. It also passes through the output gate to calculate the hidden state. Notice how the equation to calculate CT in LSTM is similar to how HT is calculated in GRU. Let's start by understanding the architecture of LSTM. This figure shows the repeating model of an LSTM architecture. Let's zoom in and look at the single LSTM model. LSTM has 3 gates: forget gate, input gate, and output gates. Forget gate decides what information is discarded from the cell state. Input gate decides the new information that will be added to the cell state. Output gate determines what the hidden state, HT, for the current time step should be. Now that you are familiar with the components of LSTM, let us understand how it functions. At a particular time step t, the LSTM hidden layer receives 3 inputs: the hidden state or output from the previous time step, ht-1, the current input, xt at time step t, and the long-term memory or the cell state c t-1. These are used to produce 2 outputs: the cell state ct at the current step t and the hidden state ht. Let's break down each step at a time. At time step t, the previous hidden state ht-1, the current input xt, their respective weight matrix and bias term pass through a sigmoid function. To calculate the vector for get gate fg, please note that every gate will have its own weight. If you recall, this equation is quite similar to the GRU gate equation. Because of the sigmoid function, the value of fg will range from 0 to 1, indicating how much of each component of the cell state should be considered. Then the action shifts to calculating the input gate, which decides the new information that needs to be added to the cell state. As you can observe, the calculation of the input gate is very similar to that of forget gate fg. Simultaneously, a tanh layer creates a new candidate vector c cap t, which contains potential new values to be added to the state. This is calculated in exactly the same way as hidden state is calculated in RNN. These values are not actually added to the state yet. They are proposed updates. The equation for the candidate vector is shown on screen. After this, we update the cell state. The cell state is updated by multiplying the forget and input gates with the cell states of previous time step and candidate cell state of the current time steps, respectively. The old cell state ct-1 is element-wise, multiplied by the forget gate output dropping values that the forget gate deems unimportant. Then, the input gate is element-wise multiplied by the candidate value c cap, determining which new values are added to the state. Lastly, the output gate's role is to decide what parts of the cell state should be used in the hidden state ht. The output gate is calculated in the similar fashion as the other gates and is used to calculate the hidden state as shown here. With that, we conclude the functioning of LSTM. Just like GRU, LSTM also reduces the problem of vanishing gradient in RNN. Just like RNN, we can implement multi-layered and bidirectional LSTMs in GRUs as well. Now the key question is where to use LSTM and where to use GRU. There isn't a common consensus on where to use each. While GRUs are slightly faster since they have 2 gates compared to 3 in LSTMs, LSTMs are older and have a robust proven record. For some, it boils down to personal preference. Next, let us implement LSTM in the Jupyter Notebook.
Let's create an LSTM model and see if it improves our model and aids Pixel Games in classifying the game reviews. The Sentiment LSTM class implements a sentiment analysis model using a bidirectional LSTM network for analyzing game reviews. It is designed with configurable parameters for input size, hidden size, output size, number of layers, and includes a dropout rate and leaky ReLU slope. The LSTM layers handle input sequences utilizing dropout for regularization and a fully connected layer to convert the LSTM output to the required output size. The forward pass initializes 0 states for both hidden and cell layers, processes the input through the LSTM, applies leaky ReLU and dropout, and outputs predictions through a sigmoid function for binary classification. And we can see that our bidirectional LSTM with 2 layers is the best performing model. With that, we have come to the end of this video. Our best performing model is the GRU bidirectional model, so we will use it to check the performance on the test dataset. Let's do that. Let's prepare our test data and apply the best model, which is the saved GRU bidirectional model. We will reinstantiate the GRU model structure that we created earlier. Now that the model is initialized, we will feed it with the trained weights. On our test data, we are getting a decent score of 83%. Phew, that was exhausting, but too much fun, right? We have covered the entire RNN network relevant for building classification model.
Previously, we went through the various types of RNN. The pixel games problem was a clear example of a many-to-one problem, where the input, which is the user_review, was sequential text data, whereas the output was non-sequential. Many-to-one RNNs are not suitable to solve problems like machine translation, question answering, code generation, or text summarization, where the output is expected to be sequential for sequential input data. And this is where many-to-many RNN models come in. These models process input sequences of varying lengths and produce output sequences of varying lengths. They are also known as sequence-to-sequence or sec-to-sec models. From Google Translate to voice-activated search, the applications of sec-to-sec models have been transforming our lives from many years. If you recall, the many-to-many architecture on the left is suitable for tasks such as NER or POS tagging tasks. In these tasks, we expect to get an output for each input word. The many-to-many architecture on the right is suitable for tasks such as language translation, summary generation, question and answering, text generation, etc. In these tasks, it is important to understand all the context from the input sequence before generating an output. Most key developments in the field of NLP in the last decade are due to research conducted to improve performance of models in these tasks. Therefore, we will also be focusing on these tasks in the rest of the course. The many-to-many architecture was one of the key architecture used to solve text generation tasks. Many of the current architectures in use today are inspired from this architecture. Therefore, we will start our text generation journey from this architecture. This architecture can be represented simply by the diagram on the right. It is popularly referred to as the encoder-decoder architecture. At a very high level, the encoder-decoder model typically consists of 3 main parts: an encoder, a decoder, and a connecting vector named encoder state. Let's break down what each part does. The encoder takes in the input sequence and transforms it into the encoder state, which is the final set of vectors produced by the last time step of the LSTM encoder. The encoder discards the output produced at every time step and preserves only the encoder state. The encoder-decoder architecture can be created with using simple RNN and GRUs as well. However, most research articles used a bidirectional LSTM to create the encoder architecture. The encoder is built in such a way that it's expected to encapsulate the whole meaning of the input sequence in the encoder state to help the decoder generate relevant texts. The decoder is typically built using unidirectional LSTM layers and takes the encoder state as an input. The decoder generates output one time step at a time, feeding in the output generated from the previous time step to the next time step. Under the hood, the encoder-decoder model is quite simple. Think of the model as 2 LSTM models with some connection between them. Now, let us walk through the working of this architecture once again using a text translation example. We will take an English to German translation example where we expect our model to translate the English phrase "How are you?" into German as via get SDR. Let us begin. The process will start at the encoder block. The encoder part is an LSTM cell. The encoder LSTM model processes the input sequence at each time step and captures all its information in the encoding state ES. In the first time step of the decoder takes encoder state ES as input along with the start token. The start token is often represented by a word index of token 1 and indicates to the decoder that it needs to start creating the output sequence. These inputs are used to predict the first word of the output sequence, WIE. At time step t equals to 2 of the decoder, the hidden layer gets 3 inputs: the previous hidden state, the previous cell state, and the previous output way as the current input. And the output of this sequence is expected to be the second word of the output sequence, get. The previous output is provided so that the output at time step 2 can generate text based on the relevant context. And similarly, the output at each time step is fed as input to the next time step. This continues till we get the end symbol, which is again a special token like start used to mark the end of the output sequence. The end token is often represented by the word index 2, and as you know from previous module padding, is often represented with the word index 0. Note that these special symbols need not necessarily be start, and some people refer to them as SOS and EOS, where SOS stands for start of sentence and EOS for end of sentence. These can be any strings given that these are not present in our vocabulary, so the model doesn't confuse them with any other word. With that, we get an overview of the encoder-decoder architecture. Before we jump to hands-on, let's understand some other nuances of the architecture. Our raw data is X. How are you? Which is to be translated into German, largely true, via get SDR. We would need to add the special tokens start and end at the start and the end of our target sequence. Next, the input and output are vectorized using pre-trained word embeddings. However, for ease of understanding, let us assume we are using one hot encoding for vectorization. For simplicity, let's assume that English and German vocabulary is limited to the example that we have discussed. So the one hot encoded vector of our English and German sentence may look like this. An important concept which significantly improves the performance of the encoder-decoder during training is teacher forcing. In teacher forcing, we feed the true output and not the predicted output from the previous time step as input to the current time step. To understand this, let's look at the first iteration of training. Here, we have fed our input sequence to the encoder, which processes it and passes the encoder state to the decoder. Before moving on, note that in the decoder, at any time step t, the output yt_pred is the probability distribution over the entire vocabulary in the output dataset, which is generated by using the softmax activation function. The token with the maximum probability is chosen as the predicted word. Let's understand this by going through time step 1. In time step 1, the vector 1, 0, 0, 0, 0, 0. For the word start is fed as the input vector along with the encoding state. This tells us that our model thinks that the probability of first token in the output sequence being start is 0.02, way is 0.12, get is 0.36, and so on. We take the predicted word to be the one with the highest probability. Hence, here the predicted word or token is get with a probability of 0.36. We know that at time step 1, the prediction should have been V, but our model is giving a prediction as get. Now, should we use this predicted value get as the input in time step 2? We can do that, but in practice, it has been seen that this leads to problems like slow convergence and poor performance. Thus, teacher forcing came into existence to solve this. In teacher forcing, we feed the true output and not the predicted output from the previous time step as input to the current time step. That means the input to the time step 2 will be y1 underscore true, which is way, and not y1 underscore pred get. The same process continues for all the time steps. Finally, the loss is calculated on the predicted outputs from each time step, and the errors are backpropagated through time to update the model's parameters as usual. The loss function used is the categorical cross-entropy loss function between the target sequence, or ytrue, and the predicted sequence, or ypred. And that is it. With that, we have understood the final nuances of the encoder-decoder model to solve sec-to-sec problems. Let's start implementing encoder-decoder architecture in a problem related to headline extraction. In the fast-paced world of news and media, the Global Times Daily, a renowned and widely read newspaper, is committed to delivering top-notch content to its audience. With an expansive archive of articles and a continuous influx of news stories, there's a pressing need to streamline the process of headline generation to enhance accessibility and engagement. The newspaper seeks to leverage the power of machine learning to automate and optimize the extraction of headlines using its vast collection of articles. Your mission is to develop a cutting-edge machine learning model that automatically generates compelling and accurate headlines for the Global Times daily articles. This tool will revolutionize how the newspaper processes content, making it more efficient and reader-friendly. You will be provided with a dataset curated by the Global Times Daily, containing 2 columns. Headline and article. Headline contains the original headlines of the articles, crafted by the editors at the Global Times Daily. Article contains the full text of the news articles, ranging from international news to local stories. Now that we understand the problem statement, let's jump to the Jupyter Notebook and create a solution for Global Times Daily.
Make sure you are connected to the T4 GPU. You can do that by clicking on the drop-down and clicking on Change Runtime Type and select T4 GPU. We will begin with importing the relevant libraries. The last line in this checks if a CUDA-enabled GPU is available for PyTorch to use or not. Now, let's read the data. The encoding is equal to Latin-1 handles any encoding issues typical with text data, ensuring characters are read correctly. Then, we define a function to pre-process text data. It standardizes text by converting it to lowercase, removing non-alphanumerical characters, normalizing to decompose Unicode characters, and stripping non-ASCII characters by encoding to ASCII and decoding back to UTF-8. This prepares text data consistently for further processing or analysis. Using ASCII format in text processing is important because it ensures the text data consists only of a standardized set of characters, which simplifies encoding and decoding processes. ASCII covers 128 specific characters, including the most commonly used letters, digits, and symbols in English. This uniformity helps avoid complications arising from the broader range of characters in other encodings like UTF-8, which includes special and non-English characters. Consequently, using ASCII can reduce errors and complexities in text processing tasks as well, especially when handling large datasets or integrating systems that may not support wider character sets. Next, let us apply the pre-processing function to both the headlines and the text columns of the dataset. We can see that the pre-processing has been applied. Now, let us define a vocab class for managing vocabulary in a language model. It initializes special tokens PAD0, SOS1, and EOS2. The class dynamically maps words to unique indices and counts their occurrences. It also tracks reverse mappings from indices back to words. The add_sentence method breaks a sentence into words and updates the vocabulary with each word, while the add_word method updates mappings and counts for each individual word. You can read the detailed description of this below in the code. Feel free to pause the video and go through the explanation part of things. Next, let us create an instance of the vocab class and populate it with words from both the text and headlines. The vocab.n_words is a property of the vocab class that keeps track of the total number of unique words identified in the dataset during the pre-processing phase. This number includes special tokens such as SOS, that is start of sentence, and EOS, that is end of sentence, which are often used in sequence-to-sequence models to indicate the beginning and end of sequences respectively. Let's run this cell. We get almost 120,000 unique words. Now, let us calculate and store the length of each text and headline entry in the dataset. After that, we check the maximum length of headlines and text. We can see that the pre-processed text has a maximum headline length of 18 characters and text length of 92 characters. Based on this, let us set the maximum lengths for the input sequences and target sequences slightly above what we got. This will standardize the length of sequences for training. Here I have set max length input to 100 and max length target to 20. Now let us define two functions to convert sentences into tensors of indices. The indexes from sentence function converts a sentence into a list of indices based on the vocabulary. And the tensor from sentence function takes a vocab object and a sentence, uses the indexes from sentence function to convert the sentence into a list of indices, and then appends the EOS token, that is the end of sentence token, to this list. It then converts this list of indices into a PyTorch tensor. With all this done, now let us create the getDataLoader function, which prepares a dataset for machine learning training by converting text and headlines into indexed sequences with end-of-sequence tokens appended. It packages these sequences into shuffled batches using PyTorch's data loader, ensuring consistent sequence lengths through zero padding. Feel free to pause the video and go through the explanation for this. Now, let us define the encoder class. This class converts input tokens into dense vector representations using an NN.embedding layer, followed by a bidirectional NN.LSTM layer that captures dependencies from both past and future contexts. A dropout layer is included to prevent overfitting by randomly omitting units during training. The encoder outputs a sequence of representations along with the final hidden and cell states, providing a comprehensive context for the decoder to generate accurate translations by summarizing the entire input sequence effectively. One important aspect to note is that in this implementation, we are not utilizing pre-trained embeddings such as word-to-vec, which were discussed in Module 3 for handling sequential data. Instead, we are training the embeddings from scratch. This approach is particularly beneficial for large data sets where sufficient data is available to develop robust, domain-specific embeddings without the need for pre-trained models. Even though we do not have a very large dataset in this problem, we are using this strategy for experimentation only. This line of code initializes the encoder class defined above with an input size of 100 and a hidden size of 64. The print function call then outputs the structure and configurations of this encoder, showcasing its layers and settings for review or debugging purposes. From this output, we can see the details of the encoder class. Next, we create a tensor in PyTorch containing a single dummy sequence of 61 random integers between 1 and 99. This tensor serves as a simulated input sequence useful for testing or demonstrating neural network models like encoders in sequence-to-sequence setups. Now, we pass the tensor X through the encoder model named ENC, executing its forward propagation method. It returns two outputs, ENC_outputs, which contains the LSTM outputs for each time step, and ENC_hidden, which includes the final hidden and cell states. Further, we will extract and print the shapes of the output and hidden states from an LSTM-based encoder. Specifically, ENC hidden H shape and ENC hidden C shape retrieve the shapes of the hidden and cell states respectively, while ENC output shape captures the shape of the LSTM output for each time step. This information is useful for debugging and verifying the dimensions of model outputs. Feel free to pause the video and go through the shapes of the outputs from the encoder and what they indicate. Let's now define the decoder class. This class generates sequential outputs based on the context from an encoder. It starts with an embedding layer converting input indices into dense vectors. A unidirectional LSTM processes these vectors using states adapted from the encoder's bidirectional output. The model employs teacher forcing during training, where actual previous outputs are fed as inputs, enhancing learning stability. Outputs are passed through a linear layer, and the sequence of predictions is formed by applying a softmax function, facilitating effective word prediction in generated sequences. This architecture is essential for tasks like machine translation, where accurate sequential generation based on a context is crucial. Here too, we have provided an explanation for this code. Feel free to pause the video and go through the explanation. Next, we will generate a tensor named TGT tensor using torch.randint, filled with random integers between 1 and 99 shaped as a single sequence of 20 elements. The TGT tensor.shape statement then confirms its dimensions, ensuring it is correctly formatted for use in sequence processing tasks. The statement DEC is equal to decoder 64,100 initializes an instance of the decoder class with a hidden size of 64 and an output size of 100. This setup configures the decoder to process and generate sequences where each element's representation is a 64-dimensional vector and the vocabulary size is 100. Now, we will configure a PyTorch environment to use GPU acceleration if available, otherwise defaulting to CPU. It demonstrates how to detect and set the appropriate device and then moves encoder and decoder models to this device to leverage hardware optimization during training or inference. Then, we ensure that tensors, including encoder outputs and hidden states, along with target tensors, are transferred to the appropriate computing device, that is a CPU or GPU. This operation is crucial for aligning data location with model computations to optimize performance and avoid errors during model execution. Next, let's execute the forward pass of the decoder instance DEC. It processes the outputs and hidden states from the encoder alongside the target tensor, TGT tensor, generating predicted sequences and updated hidden states. We will now print the shapes of the decoder's output and hidden states. Decoder output's shape represents the shape of the sequence outputs, while decoder hidden H shape and decoder hidden C shape detail the shapes of the hidden and cell states, respectively from the LSTM layer. Next, let's perform train test split twice to get train, test and validation data and print their shapes. Take a look at this code. Now, let us define three functions: train underscore epoch, evaluate underscore model, and train underscore model. Here, train underscore epoch manages a single training epoch by iterating over all batches in the training data loader, performing forward and backward passes to update model weights and computing loss. The evaluate underscore model evaluates the model's performance on the validation dataset by computing loss without updating model weights. The train underscore model orchestrates the overall training and validation process across multiple epochs, logging performance metrics periodically and saving the best model on validation loss. We have also added an explanation below, so feel free to pause the video and go through the explanation if required in detail. Now, let us create a workflow for our sequence-to-sequence model. It begins by settling key parameters, hidden size at 256, batch size at 64, and n epochs equaling 10. The code then initializes data loaders for both training and validation datasets, ensuring that data is batched and ready for processing. Subsequently, the encoder and decoder are defined with specified sizes and moved to the appropriate computing device, GPU or CPU. The encoder and decoder are integral to the sequence-to-sequence model, handling input sequence processing and generating output sequences. The train model function is called to train these models over the defined number of epochs with specific intervals for printing the training loss and validating the model's performance on unseen data. This training loop is crucial for adjusting the model's weights based on error gradients and improving its prediction accuracy over time. We can see that both our train loss is decreasing with each epoch, while the validation loss decreases till the fourth epoch and then increases. Hence, the fourth epoch is the best model which will be saved. It will be visible on the sidebar under the output section. Next, let us define two functions. The first is evaluate test samples function, which evaluates a single input sequence using encoder and decoder models. It converts a sentence into a tensor, passes it through the encoder, decodes the output using decoder, and generates a sequence of words. The function stops decoding when it encounters the end of sequence token, returning the decoded words representing the model's output. The next function we define is the evaluate randomly train function. It sequentially processes a specified number of training dataset samples using encoder and decoder models. It extracts text and headlines, generates predictions using the evaluate test samples function, and calculates meteor scores. Results, including original and predicted headlines, are displayed for assessment, offering insights into the model's training effectiveness and headline generation capabilities. Make sure the NLTK packages are downloaded before you run this cell. Also, let us set the encoder and decoder models to evaluation mode to disable dropout and batch normalization layers. Then it calls evaluate randomly train to evaluate and print outputs for randomly selected samples from the training dataset, helping assess the model's performance in generating headlines based on actual news content. The predicted headlines vary significantly in accuracy, with meteor scores ranging from 0.0 to 0.51875, indicating varied performance. Now, let us see the performance of the model on the test data by running the below two cells. The top performers include a headline about Pope Francis being hit by an object during his visit to Chile, which scored a meteor score of 0.51875. Closely followed by a news item about Dubai planning a significant development project with a score of 0.44593. On the lower end, a discussion about the ambitious Paris climate goal received a meteor score of 0.0, indicating a complete miss in capturing the headline's essence. Similarly, an article about a climate change study resulted in a meteor score of 0.03846, demonstrating the model's challenges with specific topics or complex information synthesis. And we can see that we are getting very poor scores on test data as well, with only 2 articles crossing a score of 0.2. With that, we conclude building the encoder and decoder model. Next, let's understand the limitations of simple encoder-decoder model for sequence-to-sequence tasks and move towards an advanced solution. Also, we will ensure that we use NLTK meteor score on the same set of train and test data to evaluate in the next notebooks to compare the performance of the advanced solutions to this.
We know that an encoder-decoder LSTM model takes the entire sequence of tokens as input. and comes out with the encoder state representing the entire sequence as the outputs. The decoder then takes these encoder states as input, tries to understand the context of input, and generates texts one word at a time. All the burden to transfer information from long sequences from the encoder to the decoder is on the encoder state alone. If your encoder fails to capture the information correctly, the translations by the decoder will be inappropriate. For longer sentences or paragraphs or documents, the encoder state alone is not able to catch all the important information, as the decoder is unable to decide which information to give more importance or attention to at a specific time step. For instance, if the decoder needs to generate the word "ue" at the first time step, it can put more focus on the word "how" by emphasizing more on its hidden state. Likewise, to translate "you" to "dear," the decoder can pay more attention to the hidden state of the word "you," instead of going through the entire encoder state "es." This is what the attention mechanism enables. The attention mechanism enhances the decoder's attention by selectively focusing on only the relevant hidden states from the encoder. The attention mechanism is like summarizing a movie. You watch the entire movie, but when you share about the film, you don't repeat everything minute by minute. Instead, you focus on the most important plot points to communicate the story. The impact of the attention mechanism can be seen in its official paper released in 2014 titled Neural Machine Translation by Jointly Learning to Align and Translate by Dmitry Bogdanov, Kyung-Yun Cho, Yoshua Bengyo. This is a landmark paper in the history of NLP. The paper presents how attention results in better outcomes for longer sentences. As you can see in this graph, the x-axis represents the length of the sentence, while the y-axis shows the BLU score, a metric for evaluating translation quality. The model represented in this graph by blue color used the traditional encoder state, whereas the red ones used attention. It is evident from the graph, as the sentence length increases to 30 words, the BLU score decreases sharply. However, the model RNN Search 50, which incorporates the attention mechanism, maintains its BLU score even till a sentence length of 60. The research paper also plotted the attention weights, which is fascinating to see, as illustrated in the original research paper on translating from English to French. In the diagram, the x-axis represents English words, and the y-axis represents French words. For instance, the English word agreement is closely linked to accord. More interestingly, area is mainly related to zone and ella, and gives higher weight to these two words. This demonstrates how attention mechanisms greatly aid in translating text. Now that we know the impact of attention, let's see how it works. Let's take the same example where we want to build an English to German translation model to translate "How are you?" to "Wie geht es dir?" and understand the working of attention mechanism. The key component of attention is the context vector. It informs the decoder about which components from encoder to focus more on. The context vector for a given time step can be represented as C. The CI is essentially the weighted sum of the hidden states of the encoder, where the weights are represented by alpha. The weights help determine the attention the decoder wants to give to the hidden states in the encoder. We can represent these weights as Aij, where I is the time step in the decoder and J in the encoder. So alpha 1, 2 refers to the weight given to the first time step in decoder way by the second hidden state in the encoder R. At time step I equal to 1, C1 is the sum of the products of A11 and H1, A12 and H2, and A13 and H3. The hidden state with maximum weight has more say in generating decoder's output. Here, H1, H2, H3 represents the hidden states from the encoder architecture. To differentiate the hidden states of the decoder architecture, we are going to represent it as ST. Similarly, while we create C2, we will repeat the same task again by defining the weights for each hidden state. Same is repeated for C3, C4, and C5. This is the general formula to determine the context vector at time step I in the decoder due to input in encoder at j time steps. But we are left with a startling question: how to calculate these attention weights, Aij? Let us understand how to calculate attention weights by focusing on one of them. Alpha 23. Alpha 23 is the weight that the decoder should give to the hidden state of word U while trying to generate the word get. There are many ways to calculate attention weights. Over here, we will be referring to Cardano approach mentioned in the original paper. In the attention-based encoder-decoder at time step 2 of decoder, the decoder would need S1, which is the hidden state from previous time step, and C2, which is the context vector. C2 is calculated as usual using the weighted average on the hidden activation on the encoder. The weights alpha determine how much attention to pay on each hidden states. Let us understand how one of these weights, alpha 23, is calculated. Just as a reminder, alpha 23 governs the impact of the hidden state 3 on generating the second word from decoder. To calculate the attention weights alpha 23, we will consider hidden state of the word U, H3 from encoder, and the hidden state of the decoder from time step 2 S1. These two will go as inputs to a small feed-forward trainable artificial neural network to give a value E23. To make sure that alpha 21, alpha 22, and alpha 23 add to 1, the output E23 goes to softmax activation function to get the resultant value alpha 23. The same calculation is repeated for other alpha values. We recommend you to go through this explanation a couple of times to understand it better. Now that you know how attention is used in an encoder-decoder architecture, let's implement it in the notebook.
The first set of codes till creating the data loader function is the same as before, so you can implement them before you begin. Now, let us create the encoder class which embeds input tokens and passes them through a unidirectional LSTM layer. The LSTM's output and the final hidden and cell states are returned. Dropout is applied to the embedding layer for regularization. Just like before, we will be creating the embeddings from scratch. Next, let's initialize the encoder with input size 100 and a hidden size of 64. Then, we create a tensor X of size 1,61 with random integers between 1 and 100. Further, we pass the tensor X through the encoder, obtaining outputs and hidden states, and then we will print the shapes of encoder outputs, hidden states H component and hidden states C component. Now, let's define the ButNowAttention class. It computes attention weights and context vectors using ButNowAttention mechanism. It concatenates encoder hidden states and decoder hidden states, then computes attention scores. Softmax is applied to obtain attention weights, and a context vector is computed using the weighted sum of encoder hidden states. You can find an in-depth explanation below. Feel free to pause the video and go through the explanation. Now, let us define the attention decoder RNN class. It is designed to decode encoded input sequences using an attention mechanism. It incorporates an embedding layer to represent output tokens, a ButNowAttention module for context selection, and an LSTM layer to process sequential information. Further, it also has a linear layer for token prediction. During decoding, attention weights are calculated to focus on relevant encoder outputs, facilitating accurate sequence generation. Finally, it returns decoded sequence probabilities, hidden states, and attention weights. We have given a detailed explanation below for this code too. Now, a target tensor TGT tensor of shape 1, 20 is created with random integers between 1 and 100. Then, we initiate the attention decoder RNN model with a hidden size of 64 and an output vocabulary size of 100. Finally, both the encoder and decoder models are moved to a specified device. The encoder outputs encoder hidden states and target tensors, which are moved to the same device. Finally, the decoder is called with the encoder outputs, encoder hidden states, and target tensor to generate decoder outputs, decoder hidden states, and attention weights, facilitating the sequence decoding process. Now, we define the train epoch function, evaluate function, and train model function, just like we did before. Further, we split the dataset and generate a workflow for our sequence-to-sequence model with attention. Note that it will be trained on the same parameters as before. And we can see that our train loss has been decreasing, and if trained more, we can easily get better predictions. On the other hand, our validation loss is lowest at the 7th epoch, which will be saved as the best model. Now, let's evaluate the performance of the model on the train and test data and also generate the NLTK meteor scores for the same set of samples as before to make them comparable. As expected, we can see that the performance is not at par, and compared to the previous sequence-to-sequence encoder-decoder model, the score has increased for some cases while decreasing for others. Further, we can see that our meteor scores are barely crossing 0.25 when checked on randomly selected test data. Again, we highly encourage you to increase the number of epochs, run the model, and see if the model improves. Next, we will understand the groundbreaking piece of technology that is not only better for attention, but serves as a backbone upon which the current generative AI wave is flying. And the technology is called transformers.
Pay close attention because transformers are completely based on attention. And the T in ChatGPT also stands for the same transformers. The transformer was introduced in a paper named Attention is All You Need in the year 2017 by Vaswani et al. It was designed to handle problems related to sequence-to-sequence long-range dependencies. Transformers became a key part of NLP, supporting many later developments and models like BERT, GPT-2, T5, and of course ChatGPT. But why do we need transformers? To understand this, let's do a quick recap. In our previous videos, we explored the encoder-decoder LSTM model used for language translation. The encoder processes the entire sequence of tokens and outputs an encoder state, which the decoder then uses as input. However, relying solely on this encoder state to transfer information presents a significant limitation, as it often fails to capture all crucial information, particularly in longer sentences. To address this, we introduced the attention mechanism to the encoder-decoder LSTM model. A key element of attention is the context vector, which is a weighted sum of all the encoder's hidden states. Aiding the decoder in focusing on relevant parts of the encoder input rather than just focusing on the encoder state at the end. In this formula, we can see that for different time steps in the decoder, we calculate alpha for each word with respect to each time step in the encoder, increasing the computation for long documents. This slows the model. Since this model is based on LSTM, the encoder processes the input sequentially, one element at a time. And that is a major problem. Ideally, when we are dealing with huge data sets, we would want documents to be processed in parallel. A sequential process significantly slows down training, making it impractical to train a model on very large datasets. To solve this problem, a landmark solution was created in 2017 called transformers. Let us have a look at the architecture of transformers to get an understanding of its working. Okay, this is way too complex to be explained as it is. Let us break it down. One thing that we notice is it does not have LSTMs in its architecture. This allows transformer to process inputs in parallel, addressing the limitations of the encoder-decoder LSTM model. We also observe other familiar things like input embeddings, feed-forward neural networks, batch normalization. Another term we are familiar with here is attention, and seems like different types of attentions are being used. In this transformer architecture, 3 types of attentions are primarily used in transformers: multi-head encoder-decoder attention, multi-head self-attention, multi-head masked attention. To understand these different types of attention, we can categorize them into encoder-decoder attention, self-attention, masked attention, and multi-head attention. Let us understand them one by one. We will start with encoder-decoder attention. Unlike the encoder-decoder LSTM model, where calculating alpha for each word increases computational load, transformer uses matrix operations to compute attention in a faster and efficient manner. Furthermore, the calculations with dot product attention can be parallelized. Let us explore dot product attention in more detail. This is the formula to calculate the context vector in transformers. Q stands for query vector. K stands for key vector. V is for value vector, and dk represents the dimension of the key vector. We can link this context vector formula to that used in the encoder-decoder LSTM model. The term under softmax corresponds to attention weights, and the value vector corresponds to the hidden states. This should make it easier for you to understand this complex formula. Let's understand what these query, key, and value vectors are. The query vector Q represents the word or token that is trying to find out how much attention needs to be paid to other words in the input sequence. The key vector K represents the words that are being attended to. The value vector V contains the information from the input tokens that should be preserved and passed on to the next layer in the network. To calculate these vectors, we will consider the same English to German translation example. How are you? Into Wie geht es dir? Let's start with the query vector. For our English to German language translation task, we'll process the word embeddings from each word in the German sentence. In the original paper, each word was represented with an embedding dimension of 512. These 512 dimensional embeddings are stacked to form a matrix representing the entire sentence. This stacked matrix is then multiplied by the query weight matrix to produce a smaller matrix. A 64-dimensional query vector was generated in the original paper. Similarly, to generate the key vector, we'll process the English sentence tokens embeddings by multiplying them with the key weight matrix. The same process is applied to create the value vector. Note that the value vector is also generated from the embeddings of input tokens just like the key vector, but can have different weight matrix. This gives us all 3 vectors. The dot product of the query matrix and the transposed key matrix is divided by the square root of the embedding dimension of key vector. Since the dimension size of key vector in the original paper was 64, this value would come to 8. We then input the resulting score into a softmax function. Finally, we multiply the softmax output with the value matrix to obtain the final output, denoted as Z. This completes the self-attention calculation to get the resulting vector Z. This is a diagrammatic representation of how encoder-decoder attention would help the words from the decoder to focus on the relevant words in encoder. This graph shows the relative importance of words in input sequence with the output sequence. Now that we understand how the dot product attention uses matrix multiplication to compute the context vector in a computationally efficient manner, let us jump back into the different types of attention in transformer architecture. We will discuss self-attention now. Let us try to understand self-attention first with the help of an example. Go through these two sentences. The animal didn't cross the street because it was too tired. And the animal didn't cross the street because it was too crowded. What does it refer to in these sentences? In the first sentence, it is referring to the street or to the animal. It's a simple stuff for humans, but not as simple to an algorithm. When the model is processing the word it in the first sentence, self-attention allows the model to associate it with animal. And for the second sentence, it is associated with street. As the model processes each word, that is, each position in the input sequence, self-attention allows the model to look at other positions in the input sequence for clues that can help lead to a better encoding for this word. In simple words, self-attention uses the understanding of other relevant words in a sentence into the one we are currently processing. To calculate the query, key, and value vector for words within the same sentence, we will use the same approach and get a context vector. The only difference is that the query vector will also take into account the inputs from the encoder, because self-attention understands the relation between the words within the same sentences. Unlike in RNN, where hidden states at each time steps were used to understand the context. Self-attention understands the context in a more vectorized manner with efficiency. This is a graphic representation of self-attention, which shows the relative importance of words within an input sequence. Another type of attention is masked attention. Masked attention is often used in the decoder block only. Masked attention in transformer models ensures that when predicting each token, only previous tokens are considered in decoder, preventing the model from accessing future input. This is achieved by applying a mask to the attention scores, which sets the scores for future tokens to negative infinity before the softmax operation, resulting in a zero probability for these tokens. This mechanism ensures that when the model is generating the word get, the attention mechanism only considers ye, but not is and dear. This setup mimics the forward flow of human text generation, where future context isn't known. The next term is multi-head attention. Rather than thinking of it as a different type of attention, think of it as a feature which can be applied to all the types of attention discussed so far. Multi-head attention consists of multiple attention components called heads running in parallel. Each head has its own set of learnable parameters and computes its own attention scores, allowing the model to capture a diverse context from the input vectors. These heads are developed in parallel on multiple GPUs or CPUs for efficient computation. The weight matrix for multi-head attention is often smaller in size than single-head attention for efficient training. This is similar to how we create different decision trees in random forest to get a diverse perspective. Now that we understand the various types of attention used in transformers, let's move on to understand the flow of data through the complete architecture. Like other sec-to-sec models, transformers comprises two primary components, an encoder block and a decoder block. The architecture revealed in the paper utilizes 6 encoder units and 6 decoder units. Please note that there's nothing magical about the number 6. One can experiment with other numbers. Having introduced the model's primary components, we will now explore the flow of information among these components. Let's start with the flow of information in encoder. Just like LSTM-based encoder-decoder, in the first step, input is converted to word embeddings. Unlike RNNs, in transformers, the encoder receives all word embeddings of tokens in parallel. This means that the model does not inherently know the correct order of the tokens. Therefore, to capture the sequential information of the tokens, transformers use positional embedding. It integrates information about each token's position within the sequence. For each possible position, the model combines a unique positional encoding with the word embedding to create an embedding vector for every input token. These resultant embeddings contain not just the semantic information about the tokens, but also their order within the sequence. Let this resultant embedding matrix be P. These resultant embedding matrix will form query, key, and value matrix and pass through multi-head self-attention layer. We have already discussed the calculation of these vectors in the previous video. The output from the multi-head self-attention is added to the embedding matrix P from the previous step. This addition is called residual connection or skip connection. This step helps mitigate the vanishing gradient problem by allowing gradients to flow directly through the network. Then the resultant value is normalized. This step is being similar to batch normalization. The outputs of the self-attention layer then proceeds to a feed-forward neural network. The output received after first addition and normalization step and the output of feed-forward layer are added and then again normalized. As we know that transformer is a stack of encoders, the outputs of the first encoder goes as input to the second encoder, and the same process continues. In the original paper, 6 blocks of encoder were used. So the output of the last encoder goes to all the blocks of decoder. Now that we understood the inner functioning of an encoder block in a transformer, let's understand the functioning of the decoder block. While training, there are 2 inputs to the decoder from the encoder. One is the output matrix obtained from the last addition and normalization layer from the encoder, which will serve as the key matrix and value matrix for the multi-head encoder-decoder attention block. While the query matrix comes from the previous step of decoder, the second input to the decoder is the predicted text. These inputs are transformed to word embedding and positional embedding, just like it was done in encoder. Well, in the following step, instead of performing multi-headed attention, masked multi-headed attention is performed. Masked multi-head attention is like a spotlight that a model uses to focus on different parts of a sentence. It's special because it doesn't let the model see future words. After going through the multi-head masked attention, the resultant matrix is added to the original matrix of the decoder part and then normalized. This is also similar to the step done in encoder. The output from the add and norm layer, along with the output from the encoder, feeds into multi-head encoder-decoder layer. Then we add the resultant matrix to the matrix obtained from previous add and norm step, and then normalize it. Finally, the output matrix from add and norm is passed through the feed-forward network and then again added to the resultant matrix from the feed-forward layer and then normalized to get the decoder stack output. Just like there were multiple blocks of encoder, there are 6 blocks of decoder in the original paper, each one feeding to the next. The final output of the decoder stack is passed through a linear layer of neural network, followed by a softmax layer to get the predictions. That's all about the transformer architecture. You now understand the cutting-edge architecture used in advanced NLP applications. Give yourself a pat on your back. As you have seen, the transformer architecture is a very complex architecture involving several blocks of encoders and decoders. This means that training this architecture requires training millions and sometimes billions of parameters. There are several popular models based on this architecture, and it's a common practice to not train a transformer-based model from scratch, but build upon a previously trained model. That's what we are going to do in the next module. We will learn about some popular transformer-based architectures and use some pre-trained models to make predictions. Let us begin with a quick recap of key deep learning-based model developments in the field of NLP. From 2000 to 2014, recurrent neural networks or RNNs and long short-term memory networks or LSTMs were the main deep learning models being used for NLP tasks. In 2014, 2 significant research papers came out. The first, sequence-to-sequence learning with neural networks by Ilya Sutskever, Oriol Vinyals, and Kwok Wheatley introduced the encoder-decoder architecture using LSTM. The second paper, Neural Machine Translation by Jointly Learning to Align and Translate by Dmitry Bogdanov, Kyung-Yun Cho, and Yoshua Bengio, presented the concept of the attention mechanism for the first time. By 2017, the original transformer model was launched with the groundbreaking paper Attention is All You Need by Ashish Vaswani, Noam Shazier, Nikki Parmar, Jakob Uskoreit, Lathian Jones, Aidan N. Gomez, Lukas Kaiser, and Ilya Polosukin. Transformers became the foundation for various models, revolutionizing the field. In 2018, OpenAI's GPT, which is a transformers-based model, achieved state-of-the-art results across a wide range of NLP tasks. Following this, Google came out with BERT, which emerged as a superior model, outperforming others in nearly all NLP tasks. 2019 was a year marked with a lot of progressive developments. An upgraded version of GPT-2 was released. It featured a larger dataset and more parameters, demonstrating remarkable text generation capabilities. This was followed by a series of BERT-based models such as Roberta by Facebook, a Light BERT, or Albert by Google. Google also released T5, which could perform several tasks such as text classification, summarization, question and answering, etc. In 2020, the introduction of GPT-3 showcased near-human text generation capabilities with its 175 billion parameters, marking a significant advance in the field. In 2022, GPT 3.5 was released. GPT 3.5 marked the birth of ChatGPT by OpenAI, a tool which needs no introduction. This marked a lot of investment for research in the field of text generation tools. OpenAI did not stop here. GPT-4 came in 2023, and GPT-5 is expected in 2024. Other companies did not fall far behind and came out with their own large language models. Google came out with Bard, now called Gemini Pro. Anthropic came out with Claude. Mistral came out with a model. Meta came out with a popular open source model called Llama. And there were many such developments. With the amount of developments happening in the field of large language models, it's difficult to keep track of the performance of different models. Chatbot Arena Leaderboard maintains the leaderboard of top large language models. It gives Arena Elo ratings to the models. These ratings are similar to the ratings in chess. Instead of players, large language models compete, and the better model gets the better score. This image displays the rankings of different large language models as of May 5th, 2024. It lists their Arena Elo scores, number of votes, the organizations that developed them, their licensing types, and the dates up to which they were updated with information referred as knowledge cutoff dates. Take a moment to review the ranking order. You can see that the top 3 AI models listed on that day include GPT-4 and Claude. The pace of development in the field of LLMs is rapid, with new models being released every 1 to 2 months. These models are continuously improved by training on vast amount of data with numerous parameters. This makes them large language models, or LLMs. We have specialized courses for LLMs. Don't forget, transformers are still the backbone of these large language models. Let's cover one of the most popular pre-trained transformers named BERT in detail. BERT stands for Bidirectional Encoder Representations from Transformers. As the name suggests, bidirectional, BERT uses bidirectional approach, considering both left and right context of words in a sentence. Instead of analyzing the text sequentially, BERT looks at all the words in a sentence simultaneously. For example, we want to predict the suitable word in this gap. Ice melts blank, it gets warm. Being bidirectional, BERT will consider both left and right context to have a better understanding of the context and predict with high accuracy. Before understanding the working of BERT, we must know its architecture. If you recall the architecture for the transformer from the previous module, it has encoders stacked on one side and decoders on another. But BERT has only encoder units of the transformer. BERT model with 12 encoder units and 110 million parameters is called the BERT-based model. The one with 24 encoder units and 340 million parameters, which is approx 3 times of parameters used in the BERT-based model, is known as the BERT large model. In this video, we will be referring to the BERT-based model. Having only encoder units in a BERT model makes it an encoder language model. Let's understand its working within these encoders. By now, you are aware that the first step involves input embeddings. The embeddings for the BERT model are slightly more complex compared to the standard transformers. The standard transformers have token embeddings and positional embeddings, whereas BERT also adds in segment embeddings to the token and positional embeddings. Token embeddings represent individual tokens in a sentence. Positional embeddings consider the position of each token, and segment embeddings help to distinguish between the two different sentences in a single input. The segment embeddings are required to help train BERT on the next sentence prediction task. We will talk about this task in a while. BERT also requires some specific input tokens, CLS and SEP. CLS is added at the beginning of each sentence. It is used mainly in classification tasks. SEP is a separator token added at the end of sentences. Therefore, the input sentence will become CLS, I love this game, SEP. I am enjoying it, SEP. The prepared embeddings go through multiple layers of the transformer, including the multi-head self-attention and feed-forward layers, as we discussed in the previous module where we covered the complete architecture of the transformer. The output of first encoder serves as the input for the second encoder. BERT-based model consists of 12 encoders. The output of the 12th encoder is the final output. There are two key aspects related to BERT. They are pre-training and fine-tuning. Pre-training happens on large volumes of data through which the model develops a general language understanding. In fine-tuning, these pre-trained models are customized by users to be used for their specific tasks. Let's learn more about pre-training. BERT is pre-trained on a huge data of Wikipedia of 2,500 million words and on book corpus data of 800 million words. This is quite a huge number. While training the language model, BERT uses two training strategies: masked language modeling and next sentence prediction. Let's explore these strategies one by one, starting with masked language model. In masked language modeling tasks, a portion of words from each input sequence is masked and replaced with some special symbols. Then the model has to figure out these hidden words called masked words based on the contextual words. The loss function during training considers only the prediction of the masked values. During training, BERT is only concerned with predicting the masked values, ignoring the prediction of the non-masked words. Through this training, the model gains a general understanding of the language. The other pre-training strategy for BERT is next sentence prediction, or NSP. In this training, given a pair of sentences, BERT has to identify if one sentence logically follows the other or not. For example, given the first sentence, I love this game, the model should be able to predict that I am enjoying it is a more logical next sentence compared to platypus is a rare animal. This training helps the model learn logical flows of sentences in a language. We can see that MLM boils down to understanding the context within a sentence, while NSP helps BERT to grasp the relationship between sentences. Therefore, training both these strategies together ensures that BERT acquires a broad and comprehensive understanding of language, capturing both details and flow within the sentences. That's the pre-training step of BERT. After the pre-training phase, the model is often fine-tuned for specific natural language processing tasks. BERT can be fine-tuned for vast applications like text classification, sentiment analysis, prediction related to name entity recognition, POS tagging, etc. This means BERT can also be fine-tuned for game review problem to make predictions. Regardless of the model, there are three primary ways to fine-tune a pre-training language model: output layer tuning, full model fine-tuning, and feature extraction. Task-specific, output layer. Fine-tuning is one of the simplest ways to fine-tune a model. We add a task-specific output layer designed according to the nature of the task, such as classification or sequence tagging. Then we only train this added layer on the specific task while keeping the lower layers unchanged. Instead of just training the output layers, full model fine-tuning involves fine-tuning all the layers of the model. It is particularly effective when the dataset is large and similar to the data on which the model was originally trained on. Lastly, feature extraction involves extracting output from one of the higher layers of the pre-trained model, and these features act as an input for a different model to make final prediction. This is similar to how we used pre-trained embeddings earlier in the course. Now that we understand BERT, its pre-training, and how it can be fine-tuned, let's assess the performance of BERT-based models and other NLP models using a benchmark. That benchmark is GRU. GRU, or the General Language Understanding Evaluation Benchmark, is based on a set of tasks designed to test and measure the performance of models on various language understanding challenges. GRU presents a difficult array of problems that cover many aspects of language understanding, such as semantic textual similarity benchmark, question natural language inference, quora question pairs, recognizing textual entailment, etc. Let's visit its web page to check the rankings of different models. The page displays the rankings based on model performance. As you scroll down, you might recognize some models from our course, such as Albert, CBOW, Bidirectional LSTM, Bidirectional LSTM with Elmo and attention, and BERT with 24 layers. These models, however, score lower in the rankings. Humans are given a ranking of 23, referred to as the GRU human baselines. Models ranked from 1st to 22nd perform better than humans. For instance, Roberta is ranked 21st, indicating it understands language better than humans. Google's T5 holds the 10th rank with a score of 90.3. Currently, the top 5 models are Ernie in 5th place with a score of 91.1. Deberta, associated with Clever, in 4th place, also with a score of 91.1. Turning NLR V5 in 3rd place with a score of 91.2. Vega V1 in 2nd place with a score of 91.3. The top performing model is Turning ULR V6, also with a score of 91.3. As you have observed, several BERT-based models are present in this list. Next, let's use a variant of BERT called Albert to solve our gaming industry text classification problem.
The best way to find a pre-trained transformer model is using Hugging Face. Hugging Face has gained prominence through its open source contributions, most notably the Transformers library, which provides a vast collection of pre-trained models that facilitate a wide range of language understanding and generation tasks. Hugging Face's platform supports research and development in AI by providing tools for training, fine-tuning, and deploying models. Let us see how we can navigate Hugging Face and select models for sentiment analysis. First, click on the Login button and log in with your credentials. If you do not have an account, you can easily create one by clicking on Sign Up To. Once you log in, proceed to click on Models at the top of your screen. Here, we have more than 600,000 models. On the left-hand side, you can add filters based on tasks, libraries, and datasets. In tasks, let us select text classification since sentiment analysis is a form of text classification. In libraries, let's select PyTorch and transformers. Now we can see we have more than 36,000 models available to us. You can use any of these models for text classification. Let us search for an Albert model, which is a light BERT trained on a similar dataset of reviews like IMDb reviews. Here, I'm specifically going to search for a particular model. And that brings us to our next quest: how to use these pre-trained models. The way to use them is through the Inference API. These APIs help you call the model and use them. These API inferences can be used in two ways. The first is to use them directly in Hugging Face website. You can type the review here and see the label score it will assign. For example, if you type the following review and press compute, this has generated a score close to 1 for label 1. Similarly, if we try the following review and once again press compute, you will get score for label 0 close to 1. The second way to use inference is to call the model on Jupyter Notebook itself. You can click on Use Transformer button as shown over here and get the code to initialize this model. This brings us to the end of the second task. How can we use pre-trained models by fine-tuning them for a specific task? So let us now jump to the Jupyter Notebook and fine-tune this model for finding the sentiments of the review for pixel games. We will begin with importing the relevant libraries, especially the Albert tokenizer and Albert for sequence classification. The Albert tokenizer will handle the pre-processing of your text data. It converts text into tokens that can be used by the Albert model. Albert for sequence classification, on the other hand, is the model that uses Albert for sequence classification tasks such as sentiment analysis or classifying any kind of sequence into predefined categories. Let's read the game review dataset and have a look at it. Now, we will initialize a tokenizer and a model using the Albert tokenizer and Albert for sequence classification classes from the Hugging Face Transformers library. As stated, the model is pre-trained on the IMDb dataset for sentiment analysis specified by the text attack or Albert base v2 IMDb model name. Next, let's define the custom dataset class, which is derived from the PyTorch's dataset. It is used to manage the text data for NLP's tasks. It uses a tokenizer to process text into formats suitable for model input, including attention masks and input IDs, and pairs these with labels. The dataset supports efficient data handling and batching during model training. Here, I'm going to set the maximum sequence length of the tokens to 128. Transformer-based models such as BERT or Albert often have a built-in maximum length of 512 tokens. Setting the max length to 128 helps ensure that you are far from reaching this limit while managing resource use effectively. Next, let's initialize our custom datasets and set up the data loaders. And now, let's set the hyperparameters. We will keep the epoch at 30 to make it comparable to the earlier models. It is generally advised to take a very low learning rate for transformer models. For your reference, the best RNN model so far for our sentiment classification task was the bidirectional GRU model. Here is a performance that was achieved with GRU. Once again, let's ensure our device is CUDA. Now, let us set up the code for fine-tuning. The code below freezes the parameters of all layers in a model except for the classification layer. This means that during training, the weights of the frozen layers will not update, conserving their pre-trained states. Only the classification layer is left trainable, allowing it to learn from new data and potentially adapt to specific tasks more effectively. Let's also define the calculate accuracy function. And finally, let us set up the training code and get the train and validation scores. The epoch with the lowest validation score will be saved as the best model. We can see that even after 30 epochs, our validation score is consistently going down, and it has given the best model for pixel games with 84% on validation data and a perfectly fit model. Feel free to try for higher number of epochs to get even better performance, as the validation loss is still going down at each epoch. Finally, if we check the score on test data with the best model, we get an even better score of 85%. In the next hands-on, we will simply use a pre-trained model to generate headlines for our news summary dataset. We will compare the performance of this pre-trained model with our models on the same sample dataset. Let us directly use a popular pre-trained model to make predictions on the news summary dataset and compare with the original headlines using the Meteor score. Make sure you are connected to the T4 GPU. We will begin with importing the necessary libraries. As you can see here, we will be using T5 from Hugging Face's Transformers model. T5 or text-to-text transfer transformer is ideal for headline generation and extraction due to its versatile text-to-text framework, which adeptly handles various natural language processing tasks. Now, we split the dataset into train, validation, and test. Further, we initialize the T5 model for headline generation using the pre-trained model and tokenizer from the Hugging Face model repository, specifically the Michao T5 base and generate headline. The T5 for conditional generation class is used to load the model, which is designed for generating text based on input. T5 tokenizer is responsible for converting text into a format that the model can process, handling tasks like tokenizing and encoding the text into tensors. Next, let's create the generate headline function, which prepares text for the T5 model by prefixing it with headline. And then let us check the performance of the model on the test data. Here, we can see clear improvement on the Meteor scores of test data as compared to what we saw in the previous module. This is absolutely terrific. Just imagine the amount of efforts you were able to save in terms of time and code. That is the power of finding and using the appropriate pre-trained models.
You have now tried BERT and T5 on the problems that you encountered in this course. These are some state-of-art models based on transformers, although we have a separate course on large language models. Let us give you an appetizer by comparing BERT with another popular model based on Transformer GPT-1 or Generative Pre-trained Transformer. BERT was developed by Google, whereas GPT was developed by OpenAI. BERT and GPT both are based on transformers, but BERT specially uses the encoder part, while GPT uses the decoder part of the transformer architecture. BERT is a bidirectional model. That means it learns from both left to right and right to left context of words in a sentence. On the other hand, GPT takes up a unidirectional approach. BERT is pre-trained using a masked language model, MLM, and next sentence prediction, NSP, whereas GPT is pre-trained to predict the next word in a sentence by learning coherent representations of a language. BERT is more suitable for reading comprehension tasks because it is more optimized to understand the complete context, whereas GPT-1 is better for sequential text generation, making it suitable for creative writing tasks. Great job completing this course. During this course, you have explored the various aspects of NLP, such as RNNs, LSTMs, and the transformers. You have not only learned the concepts, but also implemented them in code using PyTorch. Now that you have completed this course, you are ready to learn about large language models and build applications using RAGs and agents. See you in our other courses related to generative AI. The links are in the description below.